Okay, so it is a pleasure today to have Ed Hirst tell us about machine learning, quiver mutation, acyclicity. Take it away.
Brilliant. So of course, thank you very much for the introduction, Julius. As said, my name's Ed. I'm currently a postdoc at Queen Mary, and just wanted to say again, a big thank you for the invitation. I attended the Quiver meeting during the obviously COVID period of my PhD. Learned lots of interesting things about quivers, so it's been an honor to be here speaking. But of course, my route into quivers was more down the cluster algebra mathematical connection. So that's what I'll be talking about today in this paper, which came out in November, entitled Machine Learning Quiver Mutation-Acyclicity. So it's this mutation-acyclicity is some special property of quivers that we're trying to examine with some advanced computational techniques. And of course, I'll start by thanking my wonderful collaborators, which includes Kalmani, who's a student at Queen Mary, did a bulk of the computational work here, so big up to him. Blake Jackson, who's a postdoc in Connecticut and a cluster algebra expert, and Q1, who's also in Connecticut, and he was the one who introduced the problem to me when we got started on it, and it has been very enjoyable learning about this side of the cluster algebra work. So what will I talk about? So I'll start with a refresher of cluster algebras. Like I'm sure for this community, people have done their fair share of work interacting with cluster algebras, but a refresher is obviously always underrated. And of course, if there are some students, etc., in the audience who haven't had a chance to work with them yet, a nice sort of reminder of some of the key parts needed for this talk. I'll then talk a bit about the interesting combinatoric structure that we have in the mutation process, which underlines the generation of the cluster variables. And this forms exchange graphs, which have nice connections into physics, these cybo-duality trees, which obviously members of this community really pioneered, great work related to as well. And then I'll go on to talk about the main property we have interest in this paper, which is mutation-acyclicity. I'll give its definition. I'll talk a bit about this Markov constant, which is a way of determining this property for rank 3 quivers, quivers on 3 nodes. And that's our motivation is then to sort of build on that to look at rank 4 in this work. I'll have a very uninformed stab from my experience at some physical relevance that, really just open up some questions about how this property may be linked to physics that would love to hear from the more expertise minds in this group about how it may be connected, but I'll have a go at setting that up for some fun discussion. And then I'll talk about the main result of this paper, which is a new theorem where we prove a classification for mutation acyclicity on rank 4 quivers in some restricted settings. So I'll go through the details of that and how we prove that quickly. And then I'll go on to the machine learning, which, as I say, is just some sets of some advanced computational statistical techniques that we use to try and start to build a higher rank version of the Markov constant. So we have some nice candidates that we've generated from that. So I'll talk about how we came about with generating those and what results we were seeing related to them as well, rounding off with some summary. So jumping straight into this quick refresher of cluster algebras, what is a cluster algebra? It's an algebra we all know and love, except that it has a quite special property in that its list of generators can themselves be generated from some finite set called a cluster. So to define a cluster algebra, it's sufficient to just give the information of a seed. So a seed is a cluster, so a list of variables. And if we have a rank R cluster, that means we have R variables. And paired with that, we have a quiver. So as everybody enjoys working with in this community. And the quiver here is specifically also has to have R nodes. And in the cluster algebra sense, we just think of it as some multi-die graph. So it's a directed graph with weighted edges. So we have our nodes, we have our variables. We can quite nicely just associate a variable to each node. And in terms of the data of the quiver, the part we care about for the mutation process is the skew symmetric adjacency matrix for the quiver. And this is how we define the mutation, which we use to generate all the variables in the algebra. So how does this mutation process work? So we're given a seed which has a cluster and a quiver. The first step is to pick one of the variables to mutate, one of the R. Let's say we pick the ith node. We mutate on this by changing this variable to a new variable, which is a function of the old variables and a function of the quiver adjacency matrix. It's got quite a simple form. It has terms in the numerator, one which is we look at all ingoing nodes to the node I that we're mutating from the quiver and take a product of their equivalent cluster variables with suitable powers associated to multiplicity. And then we have another term which is a monomial product from all the outgoing arrows, the clusters associated to outgoing arrows as well. And the negative just negates the outgoing arrow nature. And then the
I have a
denominator of this,
quick question.
yeah, sure.
So I have a quick question. When you have this skew symmetric adjacency matrix, can you have arrows which go back and forth between two nodes? Like an arrow
Yeah,
going
so
one way and arrow another. What would that
yeah,
mean?
exactly. So for this restriction, we consider quivers which have no loops and yeah, no two cycles. So that, yeah,
Okay, okay,
exactly.
yeah, thanks.
There's no two cycles, and then we
Cool.
just have directed edges too. So a
Mhm.
restricted set for the
Okay.
cluster algebras in this case. And then yeah, continuing then the final bit is we just the denominator of this mutation is the original cluster variable. Once we've mutated the variable, we also want to update the quiver, which defines the rule for this mutation to a new quiver. This also has some nice simple steps. The first is just reversing the edges incident to the node we're mutating on. The second is we look for two paths that go through that node and introduce edges to make that into a 3-cycle. And where this introduction of edges introduces any 2 cycles, we remove those 2 cycles. So this connects with what you were saying with this question, Julius, that for this case, what we care about in these quivers, they don't have any 2 cycles on them. Now, that's a quick run over of what the mutation process is. It's obviously a bit nicer to see it with some tangible examples, so I'll go over one of those quickly. Here I've picked the A3 cluster algebra, named so because it's a directed version of the A3 Dinkin diagram, is used to seed it. And here so our original seed, we have a cluster, because we're rank 3, we have 3 variables. We also have 3 nodes in our quiver. We're going to choose to mutate on x1 in this case of mutation. This gives us a new variable here. So the first thing we do is we look for incoming arrows. We have one coming from x0. So we have a term with just x0. We look for outgoing arrows. There's one connected to node 2. So we have an x2. And then our denominator is just what the original variable was, which is nice and simply just x1 here. That's the updating of the quiver now, or of the cluster, sorry. Now we want to update the quiver. So nice and straightforwardly, first step is reverse the arrows incident to node 1. So where we had 0, 1, we now have 1, 0. Where we had 1, 2, we now have 2, 1. And then we look for 2 paths through that node. So we have a 2, 1, 0 path. We add an edge to make that into a 3-cycle. So we have 2, 1, 0, 2, 2, 1, 0, 2 as a 3-cycle. And then we don't have this edge introduction hasn't made any 2 cycles, so we have nothing to remove there. Now, the first nice thing to say about cluster mutation is that the process is an involution. So if we were to take this new seed, which is this new cluster and new quiver, and mutate again on x1, this would go back to the original seed. So you can sort of see this because the new numerator for mutating on x1 would again have an x2 and an x0 term. And then dividing by this variable, that would cancel where this numerator becomes the denominator, and this x1 double division becomes the term we have. And then again in the quiver, reversing arrows is our first step. This obviously is an involution. And then where we would have a new two path going 0, 1, 2, we would add an edge to make 2, 0, and this would give a 2-cycle, which we then remove. So we go back to this A3 quiver as well. So in this sort of it's a nice property of cluster mutation, or is that it's an involution, so we can always undo it there. Now, important thing to stress as well is that the first thing we did is we made a choice. We picked to mutate on variable 1, node 1, where we could have chosen to mutate on any of them. So if we wanted to package our seed into some abstract node, so this node in the center would be affiliated to this cluster and this quiver all in one. We chose to mutate on node 1. This gave us a new seed with a new cluster and a new quiver. But we could have equivalently chosen to mutate on 0 or mutate on 2, and this would give us different seeds as well. After we've mutated on 1, we could mutate on 1 and go back to the origin, or we could mutate differently on 0 or 2. And in this way, we keep generating new seeds with different combinatorics of the mutations in different orders. And this is how the generation for the cluster algebra variables works. The idea would be that you would perform this mutation exhaustively to produce all possible seeds. In some cases, this could, in many cases for algebras, this could be infinite. And then the union of all the clusters, which there will obviously be lots of repetition, will give you all of the variables that are used to generate your cluster algebra. limiting case where this cluster algebra, each mutation gives you new variables and new quivers. This exchange graph, which is this abstract graph, would end up looking like a tree. There'd be no repetition. But of course, as you'd expect, there'll be certain scenarios where you have some commutative actions in the mutation and you end up reproducing the same seed. Here's a nice example there. So there become some different limiting cases where you have some sort of non-trivial structure where you get away from this tree-like behavior. And this is a bit of a shameless plug for some work from a couple of years ago. This paper from myself and collaborators, we look in some more detail at the proper network structure of these graphs for varying different algebra types and create some new conjectures related to that. But of course, that's other work for another time. That's cluster algebras. What we're really interested in here for this paper is this property known as mutation-acyclicity. So it's quite a straightforward property to talk about. What it's effectively saying is that if I were to give you any random quiver, does there exist some sequence of mutations that would take that quiver to one which is strongly acyclic, i.e. there are no directed cycles in the quiver? This turns out to be quite an important property in the mathematics. It's certainly not an area I'm an expert in how it's used, but my collaborators are very well motivated to search for quivers which are mutation acyclic. There's some connections with path algebras that I can have a go at motivating quickly, where path algebras, which are over mutation acyclic quivers, these have finite dimensional vector spaces. So it's already pretty powerful. If you know the path algebra you're working from comes from a mutation acyclic quiver, then you're working in finite dimensional space. And then, as I understand from what they've told me, the connections to Artin algebras and your Morita equivalence between them would then become finite maps as well. So it becomes much more powerful. You're working in finite spaces, which is very useful. Another example they've told me about, which they work with, is that acyclic quivers admit reddening sequences. So, and that, from what I understand, reddening sequences give you explicit formulas for computing refined Donaldson-Thompson invariants. So if you're working over with a quiver with something that is mutation acyclic, then you already have very quick ways to compute these invariants, which can be particularly useful for the mathematicians in those areas. It's
So
definitely. Oh
if
yeah.
it's mutation acyclicity, or if it's NMA, if it's MA, that it's easy to compute these CT invariants.
If it's MA, mutation acyclic.
If it's MA, okay,
Yeah,
good, thank you.
exactly. So we want to be able to identify this property. But yeah, as you say, the property is a Boolean property. So there is a bit of a substituting MA and NMA in my talk here. So apologies if that becomes confusing. But anyway, yeah, so that's the property. Does there exist some path which of mutations that makes it strongly acyclic? And the conjugate of that is non-mutation acyclic, which says that no matter how many times you mutate the given quiver, there is no way to produce a quiver which is acyclic. And what is known about these already? Well, if we start from lower ranks and work our way up, rank one nodes, because we don't allow loops, this is just a trivial single nodes quiver. So trivially, there are no edges, so it's acyclic. So we have no non-mutation acyclic rank one. Rank two, also trivial because we don't allow two cycles. We have no cycles allowed in rank two. We just have a single edge of varying weight of infinitely many possible weights. So there are also no non-mutation acyclic quivers in rank two. In rank three, we have our first non-trivial scenario, three node quivers. And here we have infinitely many of them. There's one particularly important one, which turns out to be very useful for the proof we do later in the work, hence we're putting this 1 star. And that example is the quiver, which is the 2-2-2 quiver. So it's a 3 cycle where each edge has weight 2 between the 3 nodes. And yeah, this is an example of something that's non-mutation acyclic. And in fact, importantly for rank 3 is that there is this Markov constant, which I'll talk about on the next slide, which is a function of these edge weights. So it would take 2-2-2 as the inputs. And then there is an inequality based on the output of this function that tells you whether or not any quiver on 3 nodes is mutation acyclic or not. So a really powerful thing to know for rank 3. And importantly, for rank 4 or above, an equivalent of this is unknown. So this is our motivation for this work, is we want to start to make some steps towards trying to build what this would look like in rank 4 and above. Now, that's not to say things in rank 4 aren't known at all. There are sets of where people have been able to prove things to be mutation acyclic or non-mutation acyclic. although there are some examples that people know to be, an important theorem for verifying that is from this paper from Martian collaborators, which we use a lot in our theorem. And this says that a quiver is non-mutation acyclic if it has a full subquiver, which is also non-mutation acyclic. So if you can take some subquiver of nodes, which for rank 4 means we're looking at rank 3, and we can see that there's a quiver which is known to be non-mutation acyclic, then the full rank 4 subquiver is also non-mutation acyclic. And this applies to the general rank as well, so a very powerful theorem about connecting different ranks. To give another tangible example, on the left, I give an example of a quiver on a rank 4 quiver, which is mutation acyclic. In fact, it's a trivial case of mutation acyclic. It's actually itself acyclic. There are no directed cycles in this. You can see you could pick to start at any node, and following the direction of the arrows, there's no way to return to that node. So this is a acyclic quiver, which is then also by nature mutation acyclic as well. Whereas on the right, here we have an example of a quiver which is non-mutation acyclic, and this is we can show this through this theorem from above, where if we take the full subquiver on 0, 3, 1, this is a 3-cycle with edge weights 2, 2, 2. So it's this special known example for rank 3 non-mutation acyclic quivers. So we know that this rank 4 quiver is also non-mutation acyclic. Of course, that's just a couple of introductory examples to give a feel for the real difficulty of this problem. Here's a selection of some other ones, which of course I won't make anyone have a real go at, but in your head you can have a look and have a guess which you think are mutation acyclic and which ones aren't. I'll put you out of your misery, not that I'm sure anyone was, but the one on the far left, this is an example of one which is non-mutation acyclic. And maybe for the keen eye, you might have seen we have this 2, 2, 2 cycle, which we were showing in the example before. So we know this sort of directly from this theorem that this is non-mutation acyclic. The next one in, this is an example of something that is mutation acyclic. So we do have directed cycles here, so it's not acyclic itself. We have this 53, 39,100, and 738 cycle. So it's a directed cycle, it's not acyclic. But I can tell you I generated this by starting with a quiver that was mutation acyclic with low edge weights. And after, I think, 4 mutations, it produced this quiver here. So you sort of get a feel for the combinatorics of how quickly these edge weights can grow with mutation. So really only a few steps away in these potentially infinite exchange graphs, we can get we're working with integers that become very hard to see how we can combinatorially combine them to try and remove edges to make this acyclic. The next one in, this is another example of something that is non-mutation acyclic. Again, this has cycles, so we know it's not acyclic, but it doesn't have any 2, 2, 2 cycle or n, n, n cycle that we can see directly means it's non-mutation acyclic. But I'll tell you, it's a couple of mutations, maybe 3 mutations away from this one on the left. So again, just a bit of motivation for as you start to go even fairly shallow into these exchange graphs, we're starting to work with numbers of these edge weights that become quite hard to see directly. And this one on the right, just to keep things even, we've had 2 non-mutation acyclic now. This is a second mutation acyclic case. Again, it has a cycle 4, 2, 1. But if you perform, I think, 2 mutations, you can remove this cycle to produce something that's acyclic itself. So this is a mutation acyclic case. So I say that's just some motivation for why this is a hard problem. Certainly, you could be presented with quivers that are kind of quite complicated, have quite large numbers. It's hard to see how the exchange graph will develop. But for rank 3, as I was saying, importantly, there is a constant known as the Markov constant, which is a mutation invariant, and it can determine this mutation acyclicity property. So if we're looking at a rank 3 quiver, this is 3 nodes and also 3 edges. If we assign those edge weights x, y, z, the Markov constant is defined in this way, so named because it looks like the Markov equation, although not quite. It's not set to 0 and there's no 3 here. But anyway, it's similar enough that in its naming, it was given this name. And then given some generic rank 3 quiver, it's been shown that a rank 3 quiver can be shown to be mutation acyclic if this Markov constant is greater than 4, or if the quiver is in this finite list of exceptions given here. So that's sort of an important property I want to stress when we starting to look at rank 4 is that the Markov constant works for infinitely many quivers. As I say, these edge weights can be infinitely high in their integer values. But there is some finite list of exceptions where it doesn't work. But still very powerful thing to know for rank 3. Now, my attempt at connecting to some physics, this will definitely be overwritten in some discussion, I hope. But from my understanding, these quivers we're caring about, the directed quivers, these are sort of nicely interpreted in terms of 4D n equals 1 quiver gauge theories, where Seiberg duality between different quiver gauge theories can be shown to be the cluster mutation process on the quivers, connecting those quivers. And of course, that was work pioneered by members of this community, absolutely, and Ami's done loads of excellent work with Seiberg duality trees, looking at these exchange graphs as well. But beyond that, then what does this mutation acyclicity property mean? Well, my attempt at looking at that is that, from my understanding, n equals 1 theories, their superpotentials are defined by gauge invariant operators, which are defined from cycles in the quiver. So if you're given a quiver and you know it to be mutation acyclic, or you can determine whether it is, this would say that this gauge theory you're considering is IR equivalent to a theory which has no gauge invariant operators. And I think maybe that's fair to say it would have no sort of sensible superpotential to write down, although definitely open to being corrected there. So yeah, I don't know how interesting that is. Maybe it isn't, but that seems like a fairly straightforward or a first order connection to be making into the physics side. And the last sort of attempt I make at making some connections is that from a little bit of reading ahead of this talk, I understand the Markov equation does come up in a different context related to the physical side of thinking of quivers, where it's associated to anomaly cancellation. And this, again, a slightly better structure for the, close to the true form of the Markov equation. We have it equal to 0, although there are some different constants introduced. It does occur here, so maybe there are some similarities that can be made, setting the constants to the right values between the cluster algebra side for considering it and the physical side for considering the anomaly cancellation. And then a nice comment to make is that this paper of Ami's with Yang and some other collaborators, they conjecture a general form for higher ranks too. So it really might be that making this connection more concrete for mutation acyclicity for cluster algebras can then this form for higher rank quivers on the physics side could maybe be translated into another form that works well for mutation acyclicity for general rank quivers, which would obviously be hugely valuable for the mathematics community. So it very much might be there'll be some great physical intuition that could be very helpful to the mathematicians. But yeah, to talk now about or the main result of this paper that I'm talking about today. This was a new theorem, which I'll state what it was. So suppose we have a quiver on 4 vertices, so rank 4 quiver, with arrow weights taking values 0, 1, or 2. So we're looking at a restricted setting where the edge weights are 0, 1, or 2. Then the quiver can be shown to be non-mutation acyclic if and only if one of the following conditions hold. Either the quiver is in a mutation class with a quiver which has a rank 3 non-mutation acyclic subquiver, so there is some connection to rank 3 non-mutation acyclicity, or the quiver is a unique exceptional case called the dreaded torus. And this is an example that's already known in the literature to have some difficulty with constructions, but it's an interesting exceptional case of being a non-mutation acyclic quiver. I've drawn it on the right here. You can see that it has a cycle, the directed cycle. This 1, 2, 1 cycle is an example of one. And it's particularly interesting because it's in a mutation class of size 1. So if you were to pick to mutate on any of those nodes, you would reproduce the same quiver up to graph isomorphism. So it's which, I've had a go myself to try and prove it. You can't really, obviously not an easy thing to see by eye, but certainly a fun thing to have a go at. But effectively, because this is itself has cycles, so it's not acyclic. But anytime you mutate it, it reproduces itself, then this by nature is non-mutation acyclic, even though it has no connection to rank 3 non-mutation acyclic subquivers. So that's why it's an exception for this proof case. So how do we do this proof? Well, my expertise is really computational. So we took a very computational approach to this. Of course, looking at rank 4 quivers with edge weights 0, 1, or 2, these can be finitely enumerated. You get around 15,000 of them, which when you reduce by graph isomorphism gives you around 700, in fact 667. And then for each of these cases, we can take the quiver as a seed for the exchange graph and mutate it exhaustively on all nodes to produce depth 1, mutate each of those exhaustively on all nodes to produce depth 2, and then we keep going producing this exchange graph. And every time we produce a new quiver, we check 1, is it acyclic, in which case the original seed quiver was mutation acyclic, or 2, does it have a subquiver which is a rank 3 case of a non-mutation acyclic subquiver, in which case the original seed quiver is also non-mutation acyclic. So as you can see, it's quite a straightforward process, but since the exchange graph grows exponentially with depth, it becomes very expensive to do, and certainly impractical to do by hand. So, and to give a feeling for how much this took, we mutated up to depth 12 for a lot of cases, so we're really having to generate lots and lots of quivers. And even with lots of sort of insights and speed ups, both mathematical inspired and computationally inspired, this still took thousands of CPU hours to run. So sort of hours, a week on the supercomputer at Queen Mary, parallelized across tens of cores to generate this result for all of these 700 cases. And the output of the proof, which is quite nice,
I have a really stupid question.
Yeah.
Can you tell me like how long would this take if I would run this on my MacBook, like a standard MacBook? So like you mentioned that you're running for a week on a supercomputer with like many cores. Yeah. Like, do you have some time scale if I would do this on my private computer?
Yeah, absolutely.
Like, what is the comparison? Like, do I just multiply by 20 or something, or is it much larger?
It depends. Absolutely, it depends how many cores you use. I think this proof would probably take 2 months, 3 months on a regular laptop. But more importantly than that, because we're having to go so deep in these exchange graphs and we're having to track the lower depth to generate the next depth, your laptop's going to run out of memory at depth 5 or something like that, whereas we're going up to depth 12. Mm-hmm. So you need huge amounts of memory to be able to store all the layers to be able to do all your checks. So that's just the other obstruction to be able to do this on my computer.
Okay, cool. Thank you.
No, nice, good question. And then, yeah, a nice result of this is that we have now in the GitHub repository associated to our paper a list of all these examples from this restricted setting we consider with the classification: are they mutation acyclic or non-mutation acyclic? And this is really nice for a couple of reasons. The first is that the practical cluster algebra, the practical mathematician algebras, when they work with quivers, they often do pick quivers with low edge weights. It's a natural human thing to do, to start with cases with low numbers. So lots of those works where they want to know whether a theorem will apply, whether the quiver is mutation acyclic. We have this database already that they can go straight into and look up, is it mutation acyclic or non-mutation acyclic? Because we've done the work up front, being able to prove this. The second nice feature is that if you look, the Markov constant is the sort of the goal for rank 4 and equivalent for rank 4. But if we look at rank 3, even that doesn't classify perfectly. There's a finite list of exceptions. And despite these XYZ values being able to be potentially infinitely large, the finite list of exceptions all have very low edge weights. In fact, they all have edge weights 0, 1, or 2. So if someone, maybe inspired by some work we do here or develops upon that, hopefully, manages to find a rank 4 version of the Markov constant, and it does have a similar form in that there's a finite list of exceptions which have low edge weights, then the result of this proof gives values or gives the determination of this property for those values. So already would be very useful for doing checks against when people are searching for this. So yeah, another nice motivation for doing this proof, which our collaborators in the cluster algebra community were very satisfied by. So hence putting this paper out. Now going on to the machine learning side. So for this, our goal is to try and find some equivalent of the Markov constant for higher ranks, particularly for rank 4. This next step is the one we look at. The first thing we want to do for that is generate some more data. So we need some data to train our models with, to try and fit our equation form to. So it's quite a nice way to generate data with cluster algebras. We can start from a quiver which we know to be mutation acyclic or non-mutation acyclic. For us, for the mutation acyclic case, we take weighted directed versions of A4 or D4. So we take the dinking diagram, say the D4 dinking diagram, we add random directions to the edges, and we add random weights to the edges as well. We use this as a seed. We generate this exchange graph up to a high depth, I think around depth 7. This gives us many quivers. We repeat this for different weightings and directions, and also for the A4 type as well. And this gives us a huge set of mutation acyclic quivers that we can then uniformly sample from. So we get some long list of mutation acyclic quivers. We can repeat the same thing in the non-mutation acyclic case, now starting from examples which we know to be non-mutation acyclic. So as the example I first introduced, that if it contained, we start with some that contain the 222 as a rank 3 subquiver, and also another example known as the directed box, which is a 4-cycle with parallel equal weights. And we use this as seeds again for exchange graphs, which we generate to a high depth, and then we uniformly sample those. So this in the end gave us around 200,000 quivers which are mutation acyclic and 200,000 which are non-mutation acyclic. And each of these has an associated label because we know from the generation process that whether it's mutation acyclic or not. This is the data we want to work with. Now we want to try and train some model taken from machine learning to try and see, can this be predicted, like even the existence of an equivalence rank 4 case of the Markov constant isn't known. So we want to try and start by giving some motivation for its existence. And for this, we use the archetypal machine learning architecture neural networks that I'm sure people have heard plenty about in other talks, as it's starting to get, they're starting to become pretty popular in lots of areas of science. So for those who don't particularly care about how they're set up, you can just think of them as general, highly parameterized nonlinear functions. For a bit more information about their structure, which tells us how we inform about the equation, they're really defined by iterated linear then nonlinear action. So your input is going to be some vector, which is this x. We do some linear action, matrix multiplication, add some other vector, and then some nonlinear action defined by a function, an activation function, which here we set to be ReLU. And then we iterate this linear, nonlinear action. So each time adding sort of more and more parameters, changing the input. And then at the very end, because for this case, we're doing a binary classification problem, we use a softmax activation such that the output of the function is going to be some probability distribution over the two classes, telling you how likely the trained model thinks this quiver is mutation acyclic. As I say, we use ReLU as our activation, which is just the simplest one. We're really picking just a simple setup, or the sort of fundamental setup. And a way, because we're using ReLU, you can think of this function as being some very highly parameterized piecewise linear function in the space. So, there's some nice ways in some other papers that these functions are connected to tropical geometry, which, is interesting other direction itself, but independent to this. And then what we're doing is we take 90% of our data here. So we take 10%, put it to the side as test data. And then that 90% we use atom optimization to train a cross entropy loss, updating the values of these weights in these parameters of the function, which there are many, many, hundreds of thousands of parameters, to try and make this function prediction as close to the true value, which we then independently test on the test data. This gave us a result of 87%, which is already very strong. So of course, on the test data, best performance would be 100%, an accuracy of 1. If on the other side, looking at the worst possible performance it could do, even someone as naive as me with no good intuition about mutation-acyclicity of general quivers, if you were to give them to me a set and I were to randomly guess, I would get them right 50% of the time. So we're looking for a number between 50% and 100%. And even with this sort of uninspired setup that's quite an off-the-shelf neural network, we're getting around 87%. So already something is being learned and being picked up on for the rank 4 case. So some promising results. And a nice thing to also mention here that even if the neural network, if we were looking at rank 3, and even if the neural network were to be able to perfectly predict the Markov constant and reproduce it, it would still not itself be able to get 100% because, as said, we have some finite list of exceptions that it wouldn't work for. So how this setup is for rank 4, we don't know. It seems very plausible that there could be some finite list of exceptions as well that puts some true upper bound on any accuracy that would be below 100%. But what that is, we don't know. Anyway, we did this first experiment as a motivation, but for anyone who's worked with neural networks, they're pretty uninterpretable. There's thousands of parameters. We don't really know what's going on under the surface, and it's hard to get some real mathematical intuition out of that. So in a way, it's less useful other than giving us some evidence for the existence in rank 4. So what we turned to next was a more interpretable architecture, which is called support vector machines. So now we change our data set to look at the data set we classified in our proof. So this list of mutation-acyclic and non-mutation-acyclic quivers. We put them through their graph isomorphism classes, such that we have 12,000 mutation-acyclic and 3,000 non-mutation-acyclic. So this gives us some quite sort of dense, symmetrically distributed set of quivers around the origin. So a nice set to start with that we can then build on looking at higher edge weights. And how does the support vector machine work? Well, um, it's a pretty simplistic style of architecture in that if we were to think of these, if we think of these quivers, we want to represent them in a way that can be considered as data. Or as mentioned before, we care about the adjacency matrix, but because the adjacency matrix is skew symmetric, the diagonal and the lower triangle are redundant information. So we just take the upper triangle as the information. For rank 4, this gives us 6 entries, so we represent each quiver that we're considering as a vector of 6 integers, and we can consider these as embedded in R6. Now, a support vector machine, in the most naive format, what it's trying to do at degree 1 is trying to fit some hyperplane equation such that it partitions R6 into two spaces, where one side, all of the points are mutation-acyclic quivers, and the other side, all the points are non-mutation-acyclic quivers. Obviously, a hyperplane being able to do this is a very naive thing to think, but fortunately, there's this kernel embedding trick from computer science where you can increase the degree of the hyperplane to become a hypersurface of increasing degree. So you can add some complexity in that way to try and find some surface which sets some inequality boundary that splits the quivers into mutation-acyclic or non-mutation-acyclic, like the Markov constant does, splitting at the value of 4 the space of rank 3 quivers. So this is what we do. We use the embedding trick, with polynomial kernels, and we take systematically just increase the degree by 1, looking at all the values. And now, because we're using a biased data set in that we have many more mutation-acyclic in this restricted setting we're working with, we change to a different measure. This is called MCC. It's very similar to the accuracy, except that it avoids problems with biased classes. So even on this data with the biased classes, if it were to be predicting perfectly, it would have an MCC score of 1. If it were to be randomly guessing, so 80% of the time it says mutation-acyclic randomly, then even this, it would have an MCC score of 0. So it's again, it avoids this bias, and we're looking at values between 0 and 1 for our learning performances. Now, some interesting results. We've got to, yeah,
Sorry,
go ahead.
Can I ask a quick question?
Yeah.
Is there a way of like enforcing this permutation symmetry in the input data by enforcing it in your R6, like what hyperplanes you can have?
Yeah, I'm sure. So exactly, reduce, you're saying quotient the R6 by the symmetry to
just
make it some
basically
cone.
enforce this permutation symmetry in R6.
Yeah,
by
sure
restricting what kind of hyperplanes you can have.
Yeah, absolutely. So I'm sure. So both comments that maybe you're going to there, either you can reduce the space that you're working with the data, and then also, yeah, a more intelligent way to go about it would be to picking sets of terms which are functions of the input edges that satisfy this symmetry already, and using that as a space to be fitting over. So yeah, absolutely, that'd be a more developed way of doing this fitting. But yeah, for us, we sort of doing this first work, we took an equivalent way of looking at it where we put the data through its class, so the data naturally satisfies the symmetry, so any working function would have to satisfy it too.
Okay, cool. Thanks.
But yeah, no, exactly. Another nice way to look at to approach this problem as well. Yeah, so our results, the odd degrees, interestingly enough, we always got MCC scores of 0. It couldn't learn anything. I think we can probably fairly attribute this to because the data is symmetric about the origin, because it's through this graph isomorphism class. Maybe odd functions aren't very good at differentiating between them. But on the even degrees, the convergence is pretty quick, so already quite nice. So even looking at degree 2, we have a MCC score of 0.4, so away from the 0 random guessing. And as we start to go up in kernel order, we add more and more complexity into our equation, more and more terms of higher degree effectively. Then this performance, the MCC score, goes up and it converges to some value around 0.93. So already very promising to emphasize, because the MCC score is centered around 0 instead of centered around 0.5 for accuracy. This 0.3 is even more impressive. It's a very good score for the machine learning that in this set, it seems to be learning very well to be able to identify the property much better than a naive human could do as well. A nice thing to add as well is that, again, because we think that it's plausible they have some finite list of exceptions, it's perhaps that these cases that can't be classified, that keep it away from 100%, maybe make up this finite list of exceptions, because again, the data set we're working with are these low edge weight cases. So perhaps these are connected too. So already some nice results for the performances, but the really particularly important thing about the support vector machines and why we chose to work with them is that they're directly interpretable. So for every equation, every hyperplane that's fitted, hypersurface, we get as output an equation which is a function of the 6 weights between the 4 nodes of the quiver. That we can then forms this hyperplane that hypersurface that splits the space. So for each polynomial degree order, we have an equation for a hypersurface which would be a candidate for the Markov constant at degree 4. So we have a long list of those for each of these degrees. As you can imagine, we're already at rank 4. Certainly when we go to higher orders, these become very long equations, hundreds of terms. So I haven't got them in the slides, but in our GitHub repository linked to the paper, we have a list of them. And our next steps now are to work with some mathematicians, use their intuition to try and look for common terms that they think are sensible in these machine-generated candidates for the Markov constant in rank 4, to try and sort of distill what we think is a likely structure that we can then test more thoroughly with the expertise of people who work in this field more frequently. So already a very nice setup that we have, and as I say, we have a nice long list of candidates that seem to work very well so far. As some bonus, some work I did ahead of this, just a little bit of extra work ahead of this talk that's beyond the work in the paper. Working with the same data set, interestingly, a lot of those equations that come out, these candidates for the Markov constant in rank 4, they're interesting. A lot of them are homogeneous. So they all of the terms are of the same degree. Now, if we look at the rank 3 case, this equation is inhomogeneous. We have 3 degree 2 terms and 1 degree 3 term. So even though a lot of them are the same degree, there's 3 of the 4 are, there's one that isn't. So we'd probably expect in rank 4, if it has the same structure, that this would also be inhomogeneous. But it's interesting the machine isn't picking up on that need. So another thing I tried was trying to explicitly enforce that by, instead of using the kernel trick, do an explicit transform in the basis. So here for each quiver, we take the upper triangle flattened into a vector of the adjacency matrix, and I transform this into a basis which is explicitly inhomogeneous, so up to some maximum degree. If we take degree 0, this is just constant. Degree 1 as our maximum, this is the constant and all the edges themselves. Degree 2, we have all of these plus the squares and the cross terms. And as you can see, this will grow combinatorically, so it becomes very expensive as we start to get to higher degrees. Running the support vector machine with a linear kernel now on this explicitly embedded space gives max degrees that look like this. So these are sort of the results I got from my quick experimentation. Low degrees are 0. We get around 0.46, maybe marginally better than what we saw with the SVM with the kernel, using the kernel trick. The odd degree seems to match that here, interestingly. And then for rank 4, degree 4 and degree 5, we're still getting around those same orders too. So it didn't give us anything particularly special there in trying to encourage the system to use the inhomogeneity. But another nice basis that I tried. So as I mentioned, I did a very quick bit of reading into this excellent paper from Ami and collaborators. And here the rank 4 version they suggest for their version of their use of the Markov equation, this Diophantine equation that's important, has a specific list of terms in it which are of varying degree as functions of these adjacency matrix edge weights. So I take these as a basis. So this vector I transform into this basis using the same terms. I don't put the constants in that they pre-specify because I want the machine to try and learn that or to try and inform what it might be, because they probably would be different in this cluster algebra setting. But it includes all the square terms, a selection 4 degree 3 terms and a 1 degree 4 term. So I tried transforming into this basis, and really sort of my naive attempt at trying to learn with this basis gave an MCC of 0. So unfortunately not as good as I thought it might be. I thought we might be able to open some doors, but really perhaps with some proper guided physics intuition from the experts in your community on this side, that might be able to make this basis better and more appropriate for the cluster algebra setting, and then start to uncover the form of this rank 4 constant that's really desired in the mathematics community. That was sort of everything I really wanted to say. To sort of round up with a summary, the main result of this paper is that we have a new theorem for classifying low edge weight quivers into mutation-acyclic and non-mutation-acyclic, which is very useful for the practical cluster algebraists. They now know where theorems apply depending on what algebras they're working over. And interestingly, in the process of performing that proof, we found there was only one exceptional case, this dreaded torus, that was already known, and there were no others that were had a different way of presenting their non-mutation-acyclic nature. The machine learning, then, we saw that this archetypal architecture, the neural network, could classify very well on quivers with very high edge weights from deep mutations for the mutation classes that we looked at. And this gave us some good motivation that there probably is some rank 4 version of the Markov constant, some support of its existence. We then turned to this more interpretable support vector machine architecture, which we looked at our proof classification data with, and we got even better results. We got an MCC score of over 0.9. And very nice, we have exact equations that come out of this for each degree we consider that hopefully we can use for some future design of the real form of a higher rank version of this mutation-acyclic constant. And then, yeah, sort of perhaps a speculative final comment is that, of course, the connections between the physics and the mathematics cluster algebras are rich and deep, and maybe there is some way to connect these Diophantine equations and their structures that are obviously very useful in the physics to this problem for mutation-acyclicity as well. So yeah, thank you very much. That's what I wanted to say. I'll do my very best at fielding any questions, and thank you for listening in.
All right, let's thank Ed. Do we have questions? About the last point that you mentioned about, like, in your bonus slide, is this MCC of 0.00. I'm a bit lost here what you do with this number. Like, what does this mean?
Yeah, so it means what I did is I transformed all the quivers I considered. I put them into the information of their edge weights into this basis. So transform to make these functions. I then plot, effectively consider each quiver as a point in this basis. So this, what is this, R10 space or something, or R11 space. And then try and find some hyperplane that separates those, such that then the equation of the hyperplane would then be a function explicitly of these numbers, which would be a perfect separator for mutation-acyclicity and non-mutation-acyclicity. So okay, yeah, in rank 3, the equivalent would be I would have a basis which is x squared, y squared, z squared, x, y, z, and then I'm trying to basically fit an equation that has coefficient 1, 1, 1, minus 1. That then defines the Markov constant and perfectly separates the data into mutation-acyclic and non-mutation-acyclic. But using this basis, unfortunately, it didn't do very well. I got MCC of 0, which means no learning. So on this restricted data set, it couldn't do very well, but that very much could be my setup of how the basis is formed.
But that was unexpected.
Yeah, I mean, I don't really have good intuition of what it would look like in rank 4, but I thought that since the Markov equation has this nice show up in physics, maybe the generalization in physics would lift to the generalization in maths. But my first naive attempt here, it didn't support that, but that doesn't mean that with some more work and some guidance it might do.
Okay, thanks.
I've got another question. Could you go back to the slide where you're showing the results of predicting whether input quiver is mutation-acyclic or
the SVM or the neural network?
The neural network. Yeah, sorry, before that.
Cool.
Yeah, your input data of quivers, is it you're sampling from just 2 exchange graphs or multiple exchange? More than 2?
Exactly. It's a load of exchange graphs. It's probably around like 6 or 8 exchange graphs a piece for each mutation-acyclic or non-mutation-acyclic.
Okay. So yeah, I guess then my question is, how does the accuracy change as you change the number of exchange graphs you're sampling from?
Yeah.
So I imagine if you're sampling from just a few number of exchange graphs, the accuracy would be higher. But if you increase the number of exchange graphs from which you're sampling from, the accuracy is going to go down.
Yeah, exactly. There's lots of connections to make there, like doing learning mutation equivalence as well as a problem, like being able to find a path that connects two different quivers through some potentially infinitely long sequence of mutations. This is already a very hard problem, and obviously one we addressed in our paper already. And I think it could even be shown to be NP hard. So in a way, maybe it could be easier if these quivers are in the same, if you have lots of quivers in the same class. Obviously, in the dream setting of setting up data, we would take 200,000 quivers from different classes, mutate them very deep into the graph hundreds of times, and then use each of those as a sample. But yeah, we were restricted by feasible computational limits to restrict to only a few classes. But I still think we picked a good number. And yeah, of course, it would be good to test how changing the number of classes changes the performances as well, how it interpolates the problem between just identifying a mutation class with one class, or really identifying this property by looking over loads and loads of different classes.
Yeah, I think that was kind of my thought or question was, I wonder whether the network is just predicting whether, well, not just, because that's also, like you say, a hard problem as well, but whether it's predicting whether two quivers are mutation equivalent or whether they're mutation acyclic or non-mutation acyclic, like which problem is harder.
Yeah, exactly. And yeah, in this case, obviously the setup we did is we do have, I think it was around 8 different classes per binary class here. So we're looking at 16 different mutation classes, I think, is the rough order to my memory. So there is a good number of classes that it can't just learn one class and then know everything else.
Yeah.
But yeah, it's definitely a very interesting point to be thinking about. There's also good motivation for looking at this other data set where we have, because of the way we've constructed it, we haven't cared really about the mutation classes. So there's loads and loads of classes in this data set already as well. Because it's very rare for quivers to stay around the same edge weight order when you mutate.
Nice, thanks.
Thanks, yeah, good question.
Cool. Any more questions? Well, then I would say let's thank Ed again. And we can go off the record.